Swayam Prabha. Digital India. Educated India.
Welcome back, my dear students, and welcome back to this course in project management. As I discussed in the last class, which was the 34th class, we said that we will discuss something about GERT or GERT and QGERT and try to basically give a very good background that how stochastic networks can be utilized. So, you may be thinking that what is the point of discussing those networks here. So, if you remember, in PERT and CPM, the main difference in PERT was there was an optimistic time, the pessimistic time, the most likely time, and based on that we found out the expected time, the variance, and then calculated the concept of what was the critical path. Then we also showed that how the crashing of the jobs could be done, keeping in mind leveling has to be done, averaging techniques, and then critical path was only different from PERT in the sense that the time was deterministic. Now, in the GERT and QGERT, we will just consider the concept where it may be possible that one of the paths or some of the paths are taken, not taken, depending on the probability of the movement of either information, or the path can be taken when you are trying to build up a project which can be launching of a satellite or trying to basically come up with a new product, whatever it is. So, we will just give very simple examples and go through the basic concept of GERT or GERT or QGERT, and I am sure people will be able to understand. In the last few sessions, we will try to deal with that in a little bit more detail. So, in the 35th and the 36th session, today being 35th one, we will try to cover those topics in a little bit slow manner and cover the fundamentals. So, as mentioned here, the activity involved networks employs PERT, which is Project Evaluation Review Technique, or CPM, and are by far the most common forms of precedence diagram. However, they do suffer from some important limitations, particularly in certain settings such as the R&D project, where the probability of trying to invest in some project or trying to basically follow some path may not be actually 100% certain, or the probability may be 0 or may be between 0 and 1. So, based on that we are trying to basically give the background. So, settings such as R&D projects, where their underlying assumption reflect the complexity of the individual project setting, based on which we can say whether the path will be taken, not taken, or what is the overall probability of the time which is being taken along that path. For example, a situation such as multiple branching, success or failure of a project, yes or no, or there are more branches, whatever it is. Probabilistic branching and repeating activities via the feedback loops. So, if feedback loops are available, if you remember in PERT and CPM, we considered the feedback loops were not there. So, now we are considering the feedback loops are there, depending on how the second stage of the work has been over. So, that will give a feedback to the first stage, so that the first stage can be improved or some other sophistication can be brought into the whole process. So, which are frequently found, continuing with the reading. So, these feedback loops which are frequently found in experimental or R&D project settings cannot be modeled in a general PERT and CPM mode. As a result, we come into realm of graphical evaluation and review technique, which is GERT or GERT, which was developed to offer an alternative diagram modeling option for projects that are faced with these additional complexities, like go, no go, yes, no, if or else, whatever be the concept, those paths are not certain, and you will take that depending on whether those paths can be traversed, cannot be traversed, whether feedback loops are available, not available. Based on that, you take the decision. GERT creates a visual method for rendering network logic to precedence diagram with the added flexibility to demonstrate network complexity to a larger extent. Like in PERT and CPM, obviously we saw that looping was not there. Then the concept of end to start was the main concept based on which we worked and found out the times. But obviously the concept of start to end to end, all these other three concepts or criteria can be included and how they can be modeled. We have already discussed, even though we solved the problem for the case where it was end to start, but other three concepts can be incorporated depending on the formula which we implement. Now, in GERT, these concepts, number one, they would be subsumed automatically, and number two, as it has been mentioned just in the previous slide, that the concept of looping would also be considered in the GERT process. Hence, one can use GERT when one wants to analyze terminal networks that, so what are those conditions and what are the main criteria based on which we will work. They contain activities that have a probability of occurrence associated with them, and we intend to find the probability that the node is realized. So, we will be basically focusing our analysis on the precedence diagram considering the nodes are the activities. So, it can be done for the arcs also, but we will stick to the nodes, because it will be easier for us to explain. So, we will consider that what is the probability of occurrence of that node occurring, considering the fact that the precedence diagrams or the precedence relationships are actually met depending on the probability which has been stated. So, obviously, there is a probability based on which we want to find out that what is the probability of that node occurring in the network. So, in the GERT also we want to analyze terminal networks that treats the plausibility that the time to perform an activity is not a constant, but a random variable. So, provided a node is yes or no, possible or not possible, we also have the time factor also coming into the picture, which means if node 2 is possible, it may also be plausible that from node 2 to node 3 there would be a probabilistic time, which we have to take into consideration in order to solve the overall network. So, and we intend to find out the conditional moment generating function for the elapsed time required to traverse between two nodes, because that will give us the overall functional form between the probability and what is the actual time taken, such that trying to find out the overall critical path, its overall average time would be possible for us. So, moment generating function would be needed, because we want to find out that what is the overall elapsed time, such that adding up the times for all the paths or all the activities which actually make the critical path would be important. In GERT, the branches of the network are described by two or more parameters. So, we will consider parameter 1 and parameter 2 are the essential ones, which is, as I mentioned in the last slide, was the probability of an occurrence. So, it says the probability that the branch is traversed or the branch or the node is realized. So, that is the first part, which will denote by probability with a number suffix, where that suffix will denote what is the activity of the job taken, or what is also the activity of the job which is being traversed, say for example, from node A to node B. So, either we use a suffix A or we use a suffix A comma B to denote. So, it is travelling from node A to node B. The next parameter is the time, which is time taken or other attributes. So, these other attributes can be anything apart from time. So, but generally we will consider for the initial network that the probability and the time are the two important things. So, it will mention the time taken or other attributes to traverse the branch if it is taken at all. So, obviously, if it is not taking, the time factor would not come, hence we would not be utilizing the concept of moment generating function to find out what is the average time. But if the node is traversed or if the node is realized, then obviously you have to find out what is the actual time based on which we will do our calculation. So, technically we will consider two parameters which are important for us, because based on the parameters we can find out what is the average time, what is the set of paths which will be followed in order to complete the overall project. So, one is time, one is the probability. So, the components of the stochastic network or the GERT processes are two things. One is the directed branches, which is the arcs, edges or transmittance. So, similarly exactly what we did in PERT CPM, we had the arcs and we had the nodes. So, directed branches are basically the arcs. Now, what is important to note that in GERT, the as in PERT also and CPM also, we will basically have a precedence diagram, but the precedence diagram in the case for the GERT may not be sacrosanct due to the fact that they may be looping. So, say for example, if you are following the loop from A to B and then coming again back to A, then the precedence relationship between A and B is not as clear as what it should be in the PERT and CPM. So, in case for a PERT and CPM, we are saying that job or activity or task A has to be finished before job B, then it obviously mean the arrow is basically leading from job A to job B. But in GERT, if there is a looping, that means after B is completed, the feedback again comes back to A, then obviously this so called precedence concept would not hold true. So, but obviously it will make things much more complicated, but it will give you a much better practical picture how things are going on. The next component in the stochastic network are the logical nodes. So, logical nodes are exactly like the one which you had the nodes in the PERT and CPM. The logical nodes are only coming into the fact because in PERT and CPM, the type of jobs or the activities which were mentioned were actually realized such that the overall project should be finished. But in the GERT, it may be possible that if the probability of actually reaching that node is 0, that node would not be realized, but considering that node is a part and parcel of the overall project, which would basically give a much better picture that how the project should be done. Now, say for example, that you have two sets of activities. Let me try to explain. Obviously, I will come with an example. So, you have activity A and B. Now, it may be possible that the project would be completed either if A is done or B is done, or both of them are done. And if both of them are not done, which means the project is not realized. So, in that case, the path starting through some source till some sink goes through A, but does not go through B, which means the job is realized as mentioned in my last statement. Case 2, starting from the source to the sink, the overall job passes through B, but not through A, still the project is realized. Third case, the overall sequence of jobs starts from the source to the sink. So, whatever the source and whatever the sink is, and completes A and B in some sequence, which means still the project is realized. And the fourth notion is that it starts at source, but both A and B are not realized, which means the project is not finished. So, hence the probability of trying to realize A or B or both of them would come into the picture in order to basically calculate the probabilities of occurrences and also the time. The second point states in this slide is a directed branch has one emanating node, that means from where it is starting, to be described later. I will come to that later on, and one terminating node, which will again I will describe later, such that particular arc or that particular directed branch or edge would basically have two sets of information. One is probability, which you see is this one, which is PA, which means probability suffix A means it is basically following the arc A, or if it is basically starting from activity A to activity B. So, obviously, the corresponding probability will be given by A to B, that is the probability, and this time t suffix A, which you now see, is basically the time taken to traverse the arc A, but if it is basically from activity A to activity B or job A to job B, hence it will be t, which is time with the suffix A dash B. Now, I will basically discuss some of the very simple logical concept, which is exclusive OR and the AND gate. Gate means basically the very simple concept of a logical operator. So, I will go with a very simple example and explain that. I am sure that would basically make things much clearer when we consider the examples in a very simple matter. So, let us consider the exclusive OR. So, an exclusive OR is a logical operation that outputs are true only when inputs differ. So, say for example, you have two operators, a gate, on and off switch sort of thing. So, consider the gates are A and B, and they can be expanded to A, B, C, D, whatever combinations are. Now, the first statement says an exclusive OR is a logical output true statement if only A is on, B is off, or B is off and A is on. So, whichever, so consider, sorry, let me rephrase my statement. A is on, B is off, and the second one is B is on, A is off. So, it means that one of them is false, another is true, or vice versa. So, let us see how it is basically notified in the table. So, the truth table, second point says the truth table of A XOR, which is exclusive OR of B, shows that its outputs are true, values are 1. So, we will consider the outputs to be true, that means the output is 1, a realized one, and if it is not true, which is a false, it will be 0, binary operation sort of thing. Whenever the inputs are different. So, let us consider how they are different and what are the actual outputs. So, input A has an information which is 0, which is false. Input B has the information which is again 0, which is false. So, false and false basically means both of them are of the same category, hence the overall result is false, which is the output which is 0, which you see the first row. The second one is that input A is 1, which is true, output B which is off, which is 0, hence as both of them are different, as per the simple definition of exclusive OR, the combined effort is basically 1. So, in the next one, if you have the input A is off and the input B is on, which is 1, then the combined one is what? One is off, another is on, but now in the third row it is just opposite to what we saw in the second row. So, in the second row A was on, B was off, now A is off, B is on, the combined overall output is basically 1, which is true. And in the last instance, if both them are on or both of them are true, which is they are of the same category, hence the overall result is false, which is 0. So, this was the exclusive OR. Now, consider the inclusive OR, also known as alternation, is basically a logical operation that outputs true if and only if one or more of its operands are true. So, this inclusive OR is basically denoted by A or B. In that case, in the last slide it was A XOR B, which is exclusive. So, the truth table here for A or B shows that the outputs are true whenever one of the input is true. So, if other is false, if both of them are true, obviously the answer would change accordingly for the last statement which I make. So, let us basically see the table and you will understand. Input A is off, false, input B is off, which is false. So, combination is always off. Now, let us concentrate on second row, third row and fourth row one at a time. The second row says input A is on, input B is off, hence the combination shows that one is on, which is A, other is off, which is B, hence the combined one is on, which is true, which is 1. The third row is exactly opposite to, opposite means the input A, B are opposite with respect to what was there in the second row. So, in this case A is off, B is on, which means A has a value 0, B has a value 1, combined one is basically one is true, one is false, hence the combined output is 1, which is true. So, you see output is 1. The last row is totally different with respect to what we had for exclusive OR or A XOR B. Here you see both input A is on, which is true, which is 1, input B which is on, which is true, which is 1, hence the combination of them is a combination of true, true, which is 1, as mentioned in the slide inclusive OR. So, obviously, you should remember The exclusive and the inclusive are different very subtly. In the first case, they are of the opposite concept, but here one of them has to be true such that to give you the result as 1. Now, we come to the AND statement. So, in AND is a logical operation that outputs true if and only if both of the operands are true. So, the truth statement is basically written as A and B. It shows that it outputs is true value. True value is basically 1 here, what we are considering, yes, no, or whichever combination you want to take is basically switch on, off. On will consider true, off as false. 1 and 0, 1 will consider true, 0 as false. Consider the colors are black and white, black as true, white as false, whatever the combinations you have, go, no go, and all these combinations. So, as A and B shows that it output values a value of 1 whenever both of this input is true. So, let us consider them. Input A, which is, and now I am concentrating on the first row, input A is false, input B is false, both of them have value 0, hence the combination of both 0 0 is 0. Second row, input A is 1, which is true, input B is false, which is 0, combination of 1 and 0 is 0. Third one is exactly opposite, that means input A and input B is exactly opposite to what we saw in the second row. So, input A is 0, which is false, input B is true, which is 1, combination is 0 as you find in the last element of the third row. And the final one which you are seeing is basically the AND one. If both of them are open or closed, depending on how you are basically trying to analyze the problem, both of them are true, A is true, which is 1, B is true, which is 1, combination is basically 1. So, I will try to basically highlight these 3 exclusive, inclusive and AND once again going through the slide. So, I am going back to the last slide in order to make things much clear. So, in this case you see 0 0 gives you an output 0, 1 0 gives you an output 1, 0 1 gives you an output 1 and 1 1 gives you an output 0. See, basically you can use plus and minus operations also. In this one 0 0, which is inclusive OR, 0 0 gives you an output 0, 1 0 gives you an output 1, 0 1 gives you an output 1 and 1 gives you an output 1. So, this was inclusive OR, the previous one was exclusive OR. Now, we come to the AND one. So, this is the AND one. 0 0 gives you an output 0, 1 0 gives you an output 0, 0 1 gives you an output 0 and 1 1 gives you an output 1. So, with this information we will try to basically come up with a clear strategy for the GERT. So, in the GERT they are basically 6 different combinations, 3 in the input end and 2 in basically the output end. So, 3 into 2 is 6. So, what are the input informations? Let us go one by one. So, if you see the first, second and the third column in this slide, the first gives you what is the concept, whether it is exclusive OR, inclusive OR or an AND. What is, and second column is basically the diagrammatic representation of the code or the node, and the fourth column which basically the characteristics which we will try to describe. So, this when I go through the 3 type of inputs and the 2 type of outputs, you will find out that it makes quite a good logical sense, considering that we have already considered the exclusive OR, the inclusive OR and the AND logics. So, the exclusive OR is basically denoted by a triangle with a vertical line onto the left. So, it means the realization of any branch. So, this is important, please pay attention here. The realization of any branch leading into the node causes the node to be realized. However, one and only one of the branches leading into this node can be realized at a given time. So, that means only one of them can be realized. So, hence it is an exclusive OR. So, if you basically follow the overall concept which we had for the exclusive OR concept, it will make sense that how it makes a clear similar concept of the logical operators and trying to bring that into the GERT network. The inclusive OR has only the triangle as in the exclusive OR without the vertical line on the left. So, it means the realization of any branch leading into the node causes the node to be realized as rightly pointed out. Now, here is what is the important fact: the time of realization is the smallest, which is the minimum of the time of the completion times of all the activities or all sets of activities leading into the inclusive OR node. So, if you have basically different times, you will basically consider the minimum of them and proceed accordingly. So, in the first one which was the exclusive OR, it was one and only one. So, you will only take one of them. In the second point, what I am trying to highlight is the importance of this statement. Second one, you will take the time realization based on the minimum fact. And now come to the AND statement of the AND logic, which is basically a half circle, and with the circular part on the left hand side as it is there. The node will be realized. So, let me read it carefully. Node will be realized only if all the branches leading to the node are realized. So, all of them have to be realized. The time of realization thus is the largest. So, if all of them have to be realized, obviously it will be only realized after all of them have been basically met, the condition has been met. So, obviously logic says you have to take the maximum time. But if you consider the inclusive OR, it will be realized the moment one of them is true, which is basically a simple concept that minimum time is the important factor which has to be taken into consideration for inclusive OR. So, again coming back to the AND concept, the time of realization thus is the largest of the completion time of the activities leading into the AND node. Now, for the output logical criteria or the relationship for the GERT one, these are the one. We have the deterministic one, which is the hemisphere, but just opposite as considered in the AND input one for the GERT, and the probabilistic one is a triangle, but the triangle is just the mirror image what we saw in the other two exclusive OR or the inclusive OR concept. So, in the exclusive OR you had a vertical line on the left, on the inclusive OR it was just a triangle, which is now just the opposite in the probabilistic one. So, obviously all these 3 into 2 combinations will be done. I am going to come to that. So, let me first go through the brief explanation of the output logical relationship. So, the deterministic concept, which is the word written in the first column, then the symbol as you see, and then the characteristics. So, characteristics reads as it is: all branches emanating from the node are taken if the node is realized, that is, all branches emanating from this node have a p parameter equal to 1, which means the probabilities are there. So, you have to add up the probabilities as the sum is 1. Obviously, that should be true because one of them have to be taken. The probability, okay. So, let me clear this because I think there would be some confusion later on when we try to solve the problem. This p parameter is basically the probability, which is the overall time duration taken for that deterministic one is basically 1. The second point is basically in the first column is for the output logical relationship is the probabilistic one. It states exactly one branch emanating from the node is taken if the node is realized. So, one of them have to be taken and the probability will be given. So, but if I go back what I mentioned just few minutes back or few seconds back, if I take all the probabilities of all the possible realizations, then the sum would technically be 1, and rightly so. So, we have 3 inputs, 2 outputs. So, let us combine them. So, now you have the GERT, the overall symbolic operators which are there. The first one you see in the first column you have the serial numbers, second column you have the symbols, the combinations of the input and output is given in the third column. So, let us go one by one. The symbol which has an exclusive OR and deterministic one is given like this, because in the first part you have the input concept, and in the second part you have the output concept. So, I am basically trying to highlight the input one with the red one and the output as the yellow highlighted one. Similarly, when I go to the exclusive or the probabilistic one, which is the second row, then it is basically a triangle, a rhombus with a straight line onto the left, which is this part. So, this is basically the exclusive OR, and this triangle which you have on the right hand side, which is basically the probabilistic part. Similarly, when you come to the third intrusive OR plus deterministic, the symbol is given in the third row. For intrusive OR or probability, you have the fourth row. So, I am sure you will understand if you once you go through the 3 input and the 2 output. The fifth one is basically AND deterministic, and the sixth one is the AND probabilistic. So, with this logical operators, I will end this 35th class, and I will strongly urge the students to please go through the concept once again, and with this we will start with how the diagrams can be drawn for the GERT network, and try to explain that in the 36th and the later on class. Have a nice day, and thank you very much.